This is topic 7, testing a claim about two population means. So one thing that you should be noticing about these hypothesis tests is that all of them follow the same 7 steps and that there's not really much different that changes within each individual problem. And actually, the changes are so small that sometimes that is the biggest problem to overcome when you are doing a hypothesis test. So let's have a look at the reference tables for this topic. We have 2 cases here. So we have a non-pooled, which I'll describe what that is in a second, and then a pooled version of this test. So the hypotheses are going to be very similar to they were when you set up the 2 population standard deviation hypotheses. So there's not going to be a number in your HO and your H1. It's going to be the equality of the 2 means, and then whichever is your alternative hypothesis based on your claim. So the first 3 assumptions are exactly the same. So we need random samples. We need samples that are independent, which means that the selection and action of one sample doesn't affect the members of the other sample. We need either a normality of both populations from the Shapiro-Wilk test, or that both have a sample size that is at least 30. And then lastly, the difference is that we have unknown population standard deviations, and the difference comes with that the assumed unequal part for the standard deviations, or that the population standard deviations are assumed equal. So in order to test this assumption right here, we actually need to do the hypothesis test from the previous section. So the reason this is called non-pooled, even though the word unequal appears here multiple times for both the STATA instructions and in the description, is that what happens is that if your standard deviations are statistically not equal to each other, then we have a special calculation for the or we keep the standard deviations separate. So standard deviation 1, whatever that sample standard deviation is, standard deviation 2, whatever that is. So we don't pool them together because they're not statistically the same, so we keep them to be separate standard deviations. However, with the standard deviations are equal, we call this a pooled test because if they're statistically the same, we can call them the same standard deviation, which actually helps reject HO. So it makes it a little bit easier to reject HO. But all that you need to remember is that you have to do this hypothesis test, check this assumption, and that if you have equal standard deviations, then you're going to leave the unequal box unchecked. And if you have unequal standard deviations, then you are going to check the unequal box. So, but this test being called pooled and non-pooled doesn't really kind of jibe with this. So I would just kind of link these 2 together. So after the assumptions, it's going to be very similar in STATA, except for that we're just going to select the correct test. We're going to be still selecting the t-test calculator, but now we're going to check the box for the 2 sample test. And then checking the box is going to be the new thing for this here. So technically we may be doing 2 hypothesis tests in our assumptions now. But again, it's an informal hypothesis test. We're going to go over exactly what you need to say for this assumption to check it, because we're going to do a little bit more than we do with the Shapiro-Wilk test for a few reasons. And then lastly, our step 7 is going to be very similar to the step 7 from the 2 population standard deviation section. So let's go back to the notes. So what I left off with is that when you're checking the assumption for whether or not the standard deviations are equal, this is called equality of variance. And so this is also not jiving with the assumption that we're checking, in that standard deviation is actually, the variance is the standard deviation squared. So I don't know, I mean, these 2 things go together, but it's not a direct link. So when I say EOV, it's going to be a kind of a jump to remember that I'm talking about testing to see if the standard deviations are equal or not. So the informal version of the hypothesis test is going to contain a little bit more than what we do for the Shapiro-Wilk test, which again is just stating the p-value and whether or not it's greater than or less than alpha. And then, of course, if you pass the assumption. So we're going to have the hypotheses, and no matter what your HO and your H1 are in your hypothesis test, you are going to be using equal and not equal to, because the assumption doesn't care whether one is greater than the other. All we care to test is whether or not they are equal or not equal. So when you're checking the assumption for this, it doesn't matter what your HO and H1 signs are for your overall two population mean test. You're going to do equal and not equal to for your standard deviations. It is important that you change the symbols. It's easy to forget and put the mu symbols here for the population means again, but we'll see that when we go through the test. The p-value, how the p-value compares to alpha. So is it bigger or smaller than the alpha from the problem? And then your conclusion about EOV. So are you concluding that the standard deviations are equal, or are you concluding that they're unequal? So there's no picture, there's no test statistic, and no step 7. So no confidence interval. We could do a confidence interval for this. It's pretty untypical that you would have to run this kind of test out in the real world in a formal sense. It'd usually be informally for checking this assumption, because this is a pretty popular test. So if you support HO, you are essentially saying that your population standard deviations are statistically equal. So that means that you have EOV, so you have equality of variance. If you reject HO, you're saying that you do not have EOV, which means that the standard deviations are not equal. So you do not put them together. You leave them as two separate standard deviations. So we'll see this a little bit better when we look at the problem. And then my last note that I have before we start looking at a few problems is the confidence interval we find in step 7 for a 2 population test is different than what we had looked at with the 1 population test. Specifically, the difference of those 2 population means is what the confidence interval is going to tell us. So if we have 10 and 20 for our lower and our upper number, then that means that whatever you've put in first, that mean minus the data you've put in second is going to have the difference of these two numbers. So that will be much easier to see when we look at an exact example. The MVD will change as well because we're not estimating a single parameter, we're looking at the difference between the two. I think the MVD actually gets a little bit nicer. A very important thing to note, I would probably underline and star this, is that we're going to start to find it very important to organize what we're calling population 1 and what we're calling population 2. So this is going to have an effect on the next, this topic and the next 2 topics. So the order matters and is very important. So I try to very clearly label all of my data that I'm using. So I always state what my population 1 is and my population 2 is. And also, if you're not clear enough when you're stating the conclusion of a problem, you might not actually end up saying what you've concluded, because if you just say, the mean of population 1 is greater than population 2, but you haven't labeled 1 and 2, I don't know if 1 is female and 2 is male, or if it's vice versa. So it's very important to be very clear with your labeling on this. And then lastly, there's going to be 3 cases with the confidence intervals that we get for step 7. The first one is that the confidence interval contains 0. So looking at this version of the confidence interval, if we're using the difference between these two, so if these two are the same number, so if we just say, okay, population 1, I think that's 10, and a population 2, that's 10 as well, then they're the same exact number, which means that their differences are 0. So if the confidence interval contains 0, then we have evidence to suggest that the population means are statistically the same, which means we're going to fail to reject HO. And HO, remember, is going to say that they're equal every time. So if they're always the same number, or we have evidence to suggest that there could be the same number in the confidence interval, and that results in a 0, then we will conclude that they are statistically the same. So we have no evidence to refute that. The other 2 cases are if the confidence interval limits are both positive, This is supporting rejecting HO because we don't have 0 inside there. There's not a sign change. And that means that population 1, whichever one you've entered first, is always greater than the mean for population 2. The confidence interval is going to be the left number, but I don't like relying on this statement, but it is always true. And then if the two confidence interval limits are negative, this supports rejecting HO, and that means that the mean for population 1 is less than the mean for population 2. So this is all very general right now, but it's important to have, heard it and read through it a little bit before we start the problems, because it will help solidify some of these kind of more picky details when we actually get to the problem. So let's look at our first one. A study was done on proctored versus non-proctored exams. This is one of my few not real data questions in this whole unit, I think. But for the 35 students that had a proctor while taking their exam, the mean score was 75.95 and the standard deviation was 11.74. So this here is one of our populations, the students that had an exam that was proctored. Then they give us a second population information, which is that 32 students took their test without a proctor, and they had a mean score of 86.49 and a standard deviation of 21.58. So one thing that you want to start to look at is that they had a higher mean, so 86.49 is definitely higher than 75.95, but they also had almost twice the variation. So because of that, and our sample size is not being too huge, although this isn't a bad sample size for means, we may end up determining that they're not statistically different. But I don't know yet, but I really like to take the whole scope of the question into account before I, just jump into writing down steps 1 through 7. They give us this little gem here, which is nice. Assume that the two samples are independent random samples. And then at the 0.05 level, so that's our significance level, test the claim that the non-proctored students have a higher mean test score than the proctored students. So the first thing that you wanted to notice is that the information given in the problem gives you the proctored students first. And the claim mentions the non-proctored students first. So this is something, if you're kind of on autopilot mode or you're going really fast, you might not catch this and you may end up switching these values around. So actually, this used to be a quiz question, and I took it off because so many students that knew how to do this hypothesis test well messed this up out of, kind of carelessness or speed, and that my quizzes are always on Fridays at the end of class, so maybe they wanted to leave early. But it's really easy to make a mistake with switching these values. So what I do is that I try to organize myself as best as possible, because I know that I'm likely to go a little bit faster since I've seen the problems before. But once you've done a bunch of them and you do get comfortable with them, you will find that you're going to start going a little bit faster, and you might lose some little details in the way. So I put this on the side so that I wanted to write my HO and my H1 exactly how they were stated in the problem. So this is my my recommendation, is that you put them in the order of the claim, because a lot of times when you come back and reread the problem, you'll emphasize the statement that has your claim in it. So this is the statement that you're more likely to come back to. So this is what I recommend basing your HO and your H1 order off from. So you could put a 1 and 2 here and label this as 1 and 2, but I think it's easier for both me, you, and anybody else that sees your hypothesis test if you have labels that are, N and P is just as, straightforward as 1 and 2 if you have a clear label. So I'm doing proctored, non-proctored, and those match up. No matter what, we're always testing to see if these population means could be equal, because remember, this is a sample from a population. This is a sample from a population. So now we actually have a bigger stretch. We're not just seeing how one population compares to a number. We have variation going on here and variation going on here. So it's pretty cool that we could have sample sizes of something that's this small for each population and still have a lot of confidence. And means are really not sensitive to sample size at all. So this is definitely a stretch further than we looked at with the one sample testing. So our assumptions, random, they tell us that that passes, and then independence, that tells us that pass. We will talk about that a little bit more in the upcoming problems. Independence can be a little sketchy sometimes, and I have a fix for that. Usually, if I have an issue with independence in any real world situation, I would have to go back to talk to the person that either provided the data, because usually I have data given to me. I'm not usually on the collecting end. Or I, say, hey, I'm not comfortable passing it at this time. So we'll talk more about that in a few problems. And then we need normal populations or sample sizes of at least 30, which is nice. We can pass this because of sample size. And then lastly is this test on the equality of variance. So you can write EOV, check, or X, but I think it's a little bit more easy to relate to if you just refer to what you're saying in your HO and your H1. So standard deviations are, and I leave that blank for a little while I do this hypothesis test. So even despite the fact that my H1 had a greater than, this hypothesis test stands alone by itself. I put it in a box to try to separate it from the problem as much as possible. So we don't care if population standard deviation 1 is greater than or less than population 2, population standard deviation 2. We only care if it's equal or not equal to each other. So that links up directly to the two cases in our assumptions, which is that they are equal or not equal. So we don't care whether they're greater than or less than. We just want to test to see if they are the same or different statistically. So let's head to Stata and we will check this assumption. So, oops, that's the next problem. Oh, it didn't resize. Okay, so the hypothesis test, so we're doing a hypothesis test, so we're going to select this first one with tests in it. We want the classical tests of hypotheses, and we are going to be doing a variance comparison test calculator. So we're not telling Stata a big list of data that we wanted to analyze. We have the summary statistics, and we want the analysis to be based off from the data that we enter. So this is going to be the variance comparison test calculator. So imagine you have a calculator and you have the numbers and you just do, 3 times 7 because you already know it's 3 and 7. But if you have a big list of raw numbers, you don't necessarily know what these are yet. Although I always recommend finding them first. So I already have this problem in here. The non-proctored students, I put those first, even though they came in the problem second, because I'm keeping the order the same. So whichever one I've entered first is going to jive with the one I've put first on my paper. Sample standard deviation for that. And this is why I write them on the side, because there's going to start to be a lot more numbers in the problem. And this doesn't take a lot of time at all, and it's very helpful for me. And then you got to, so you might only have this one when you originally look at it. So you have to select 2 sample because we're comparing the difference across 2 samples, and those samples also connect with 2 populations. So the confidence level, if we look at this, we're going to have a right-tailed test here. And so on my picture, I say left-tailed, but it's clearly a right tail. So that means we're going to have 5% in this right tail over here. And so that means that I need to double the tail to make it symmetrical. So there's not 2 tails already, so we need to make 2 to have it be symmetrical. So this is going to be a 90% confidence interval. So we need that for Stata. So this needs to be 90%. So when you hit OK, you end up getting a lot of blank stuff here, and that's okay. And then you get a p-value of the equal or not equal to of 0.0007. So you don't need to write anything else here besides the 0.0007. So this is going to be considered a low p-value compared to alpha of 0.05. So the p is low, we're going to reject HO. And so what this means is that if we reject HO, then we're assuming that they are unequal standard deviations. So we have evidence to suggest that the standard deviations are statistically different. So if you go back to here, again, you're always going to be using this middle p-value for the standard deviation test every time because, again, we only care about whether they're equal or not equal to. So it's not going to matter what you have up here. This is a test within a test. So now let's actually answer the question about the two population means. So we want to know, is there a statistical difference for the proctored versus non-proctored students? So I'm going to run this test. And this is going to be the t-test calculator. So t-test is always going to be the test that you do on a mean. And then you have the option within this to select 1 or 2. So, and I already had this problem in here. So make sure that you are connecting these here with the actual standard deviations. Because when I did this originally, I had actually switched these means out of carelessness. So it's really easy to just kind of report numbers. So now the box checking, which is one of our new things for today, is going to depend on whether or not you've assumed that the standard deviations are equal. So just remember the variance is the standard deviation squared. So if we have unequal standard deviations, we're also going to have unequal variances. So if you decide that they're not equal, they're unequal, and you check the box. So then I actually left this confidence interval in here because even though we don't get a confidence interval for this, I usually just am thinking about it at that point, so I'll set it up then. So the t-score for the two mean test is 2.45. The p-value is going to be the greater than 1, so 0.0090. This p-value is less than alpha, so we're going to reject HO. If we're getting rid of HO, our claim is H1. So think of this like a game where a sports game, like a football game or something. Only one team can win. So if HO loses, that means H1 wins, and H1 is also our claim, which you can think of as a bet you're placing. So we placed our bet on H1, and H1 won. So that means we're going to support our claim. That's one thing I'm finding that students have a slight issue with is sometimes if you reject HO, people will automatically reject the claim. But it can be, they can match. You can have reject, reject, or you can have disagreement, or you can have, fail to reject too. So we're supporting the claim that the mean of the non-proctored students is greater than the proctored students. And of course, my first question is, well, by how much? So that's what the confidence interval is going to tell us. Before we get to that, our picture here, I recommend always putting this mean 1 equals mean 2 here, which N and P would have been a little bit more specific. And what this also means is that mean 1 minus mean 2 is 0. So this is if you did an actual algebra equation and you subtracted mu2 from both sides, then you would have this second statement here. But I like to just think about this. If these two were the same number, then they would have a difference of 0. So our t-score would be about 2.5 steps above the mean, and the shaded area is less than 1%. So this isn't drawn to scale, but it is pretty small, so they should all link up. So lastly, the confidence interval for this question is 3.32 to 17.76. So remember, this isn't talking about either one of the populations specifically, it's talking about the difference between the two populations. So non-proctored students come first, proctored students come second. So honestly, I like stating this instead of saying the MVD, and you don't need to do both. So this is technically better than the MVD, and I find that people like this better at this point of the unit. So the mean of the non-proctored students' exams is higher than the proctored exam by 3.32 to 17.76 points. So, I mean, it's a pretty big difference. We could expect, maybe a 15-point difference. That wouldn't be too unlikely, or even up to 17.76. So let's try another one. I would take a moment to pause and check out the next problem. And as I say here, this problem also introduces the infamous squiggle. It's actually not infamous. It's a good thing. So take a minute to pause the video and look through this problem. So this problem is looking at the cholesterol levels for heart attack patients versus 30 other patients that did not have heart attacks. So the question is looking at us to determine if the cholesterol levels are higher for heart attack patients using a 0.05 significance level. So this is nice. They give us the data in a nice little table. So the heart attack I called HA, and the control group is the group that didn't have heart attacks. So I called them the no group, so no heart attack. So greater than is going to be that symbol. So I would put them in the order of using the symbol directly given in your claim statement. So I would put the population mean of the heart attack patients is greater than the population mean of the non-heart attack patients. So your HO is going to be the equality of the statement, and your H1 is your claim. So when you go down to the assumptions, and this is where we're going to get to the squiggle, random doesn't pass. They don't say that there's random selection. And I wouldn't pass or fail independence without getting more information. So remember, samples are independent if the selection of some doesn't affect the selection or the actions of anyone else. So the way you're going to start thinking of this is, okay, so we select 58 people. Are they all in the same hospital? Is it possible that there are, family members in there? Maybe there were, patients in the hospital that had a family appointment, or they, were in there because they were in a car accident. So if there's not compelling evidence to suggest that it's obviously independent samples, they're not going to affect each other at all, then check it. But otherwise, I put the squiggle a lot for independence. If independence fails, you can still run the test. It's not, game over at all. But if you do the squiggle, put some kind of statement as to, what your thinking is. So my initial thought was, are they family members? Another thing is that if they're using the same machines for groups of people, the machines are going to be, slightly different from each other because, again, natural variation. So that's another thing that you can say, and I'm sure there's people that know a lot more than me about this specific kind of scenario. So I really like this explanation of why you fail independence, because sometimes it really makes me think about things a little differently. So lastly, the normal populations or the sample sizes are at least 30. This fails. If this fails, it is game over for the hypothesis test. So I have a little image here. If you cannot pass this assumption, you do not keep going. The next statistics class covers a topic called nonparametric testing, and it's really interesting how it works. But it's basically tests that have no assumptions, which sounds really nice, and it's even better than it seems, because the rest of the problem is straightforward as well. So if this fails, then this does not fall under the realm of the hypothesis test that we would do, that's considered the traditional hypothesis test, which is what we do in this class. So if this one fails, it's the end of the problem. You can't do anything. There will be no long whole page hypothesis test questions on the exam that you have a failure of a major assumption. So don't expect this to happen on the test. I will put a statement about this for the Unit 4 exam description, but there will be specific questions dedicated to assumptions failing. So if you get a whole page problem on a test, I guarantee you that the assumptions will pass enough to do the problem. So I want to look at one more problem. I'm going to leave the fourth one for you to do by yourself. And this next example is from a study from the American Journal of Clinical Nutrition, and it is evaluating the calorie intake of men that were getting 4 hours of sleep a night versus men that got 8 hours of sleep a night. And so the article name itself is very long here, so I'm going to let you read it on your own. but the men participating were randomly assigned to each group. So now think about this. We have, a bunch of men, maybe they volunteer to participate, but they weren't randomly selected. However, randomly selecting the people or randomly assigning the people to the group they're participating is almost always good enough to pass the assumption. So we're going to pass the assumption if that happens. So it's not going to be a trick, but it's really good thinking if you were like, well, they have 30 people, 30 men. But if they didn't randomly select those 30 men, does that fail the assumption? And ideally, you'd want to randomly select the men as well. But it does make it a little bit better to remove some of that bias if they are randomly assigned to the groups that they're in. So we have a 0.01 significance level, and we're trying to see if there is a difference. So when you're testing to see if there is a difference, you're going to have equal to or not equal to as your HO and H1 signs. So I call this the 4 group and the 8 group. And also this, you will not be able to know until you've entered this data into Stata and had to analyze it. So that's what I started with. I wrote this down first, but then I headed right over to Stata. I will put this in the datasets folder so that you don't have to retype this. But when you're going to analyze anything, don't just, say, oh, I know what the H1 and HO are. Actually take a second to understand your situation a little bit. So my 2 variables I've put in 2 separate columns. And if you leave this blank, it will actually automatically do an analysis of all the variables. But I usually like to fill them in just to make sure I know what I'm getting. The standard display is going to be good enough because we don't need any of the quartile stuff. So I just want to know, okay, so what is this looking like? So the men that received 4 hours of sleep actually had a smaller sample mean, but they had, and a smaller sample standard deviation. So I'm pretty confident that we're going to decide that they're statistically equal because these numbers are pretty similar anyway, and they also vary in a similar way. So, I mean, we should probably see that these 2 are equal as well, if I had to guess. The sample size isn't really that big. But again, 15 is enough for a mean test. Means are, again, not sensitive to sample size at all. So, but we're going to have a bigger confidence interval because of it. So I passed random, and I said randomly assigning for the treatment is good enough. I did pass independent samples, probably unless the men knew each other and maybe they were, hanging out with each other when they were eating their calories for the day. So that should probably pass. But I'm very unstrict about this. But if you put a squiggle or anything, you should have some little justification. We either need that the populations are normally distributed or that they have a sample size of at least 30. And we definitely know that we fail sample size because there's 15 for the 4-hour group and there's 15 for the 8-hour group. So to determine if we pass normality, we've got to do the Shapiro-Wilk test. So this is under distributional plots and tests. And then this is still here from probably the last time I did this. So the p-values are very high, and this is real data. I think it's very interesting at how bell-shaped real data is. And so we get a p-value for the 4-hour sleep group of 0.9395 and an 8-hour sleep p-value of 0.8664. So this is way higher than 0.05, both of these, so this passes normality. And then lastly, the EOV test, we are seeing if they're equal or if they're different. To run this, you're going to run the variance comparison test calculator. And so then we had 15 in our sample standard deviations. So technically, since we're testing for equal to or not equal to, it doesn't matter which one we put in first. But I usually try to be really strict with the order. All right, so let's see what that is. All right, so it should be a 99% confidence interval. We are two-tailed, and alpha is 0.01. So that means we're already symmetrical since we're two-tailed, and we have 99% left over. So I'm going to fill that in now just since I'm thinking about it. Let's double check. Yep. So for the UOV test, the test to see if the standard deviations are equal, the p-value is 0.6114. So 0.6113. Okay, this is interesting. So I already had these summary statistics, but the other option that you had for this, which honestly is actually a little bit better than what I had just done, because I rounded when I plugged in these standard deviations. The difference in the p-value is going to be very small, but I think it's important since you already have your data in. See, here we go. Now I have it set up. It makes sense now. So this is going to be a 99% confidence level. Now, which one you select here, so this is if your number of calories is in one column and you have a second column that has a 4 or an 8 for which group they're in. So that's for if you have groups. But you have two separate variables, and Stata considers this a variable. This is a variable. So you have two separate columns with your data in it, and so that's going to be two groups using variables. So again, this is 99%, and this is 0.6113. Very small difference, but since the data was already entered in, honestly, that's what I should have done to begin with. And that's not something you would pick up on unless you had an answer key to compare to. But since this p-value is higher than alpha 0.01, we're gonna fail to reject HO, which means that we're saying that these standard deviations are statistically equal. So this assumption isn't a check or an X, it's just stating whether or not they're equal or not equal to. So now we get to run the actual test. I recommend the same thing where you do the t-test comparison instead of the calculator. So this is again to sample using variables. Our two variables here, and you do not check the box because we've determined that they're statistically equal, not unequal. So we're going to leave this box unchecked, and then we hit OK. And the t-score and p-value, so negative 0.45. The p-value is going to be the middle one, so 0.6595. This p-value is greater than alpha, so the p is high, HO will fly, so we're going to fail to reject HO. But HO is also our claim, so here we do agree with our decision in 5 and 6. So we fail to reject, or you can think about it as supporting HO, which in this case means that we're also going to support our claim, that there's no statistical difference in the mean number of calorie intake between the 4-hour of sleep group versus the 8-hour of sleep group. The picture, it's really easy to forget that the test is two-tailed. I didn't write it over here in this case, but what had happened is when I did this problem, because I didn't write two-tailed, which I usually do, I put in this t-score and shaded this tail, and I said, wait, that's not more than half. So then that's what made me use the picture to help me link everything together. So, okay, it's two-tailed, and basically this means that we're going to reject HO and go with H1 if the 4-hour group is higher than the 8-hour group, or if the 4-hour group is statistically lower than the 8-hour group. So this is why we end up getting two sides, even though we only we measure only one difference. So we found that the 4-hour group had a lower mean than the 8-hour group, so that's the lower one. But we double the tails because there's basically two ways that you can screw this up. So you could be too low. One could be lower than the other one, or this could be higher than the other one. So lastly, the confidence interval that we end up getting is 1048.0 to, what's my confidence level here? Yeah, it's 99. All right, I'll have to put a note on it. So off by a little bit. I feel like I wonder if I did the rounding for this one too. So since 0 is inside of this, the confidence interval supports failing to reject HO, because HO says that there's evidence to suggest that they could be the same exact population mean. And since we found evidence that their difference could be 0, that means it's possible that they are the same number. So the next problem is another real data example from a journal. So I'm gonna leave this in the answer key. If you have any questions, please feel free to send me an email. And make sure as you're going through these that you don't always just have the answer key in front of you. Try as much as possible to pause and start setting up the problems because they are very, very similar. All of the, topic 2, 3, 4, 5, 6, 7, 8, and 9. They're very, very similar. But what we're going to start to focus on is, okay, well, if we're testing to see if there's a difference in the number of calories, then the parameter we need to use is going to be the mean because that's how we summarize this data. So that's one thing that will be challenging as you do the learning quizzes and you're taking the exams because it doesn't necessarily have a section name on top. So we had the luxury of having topic 7 up here. So we know that these are all going to be tests about 2 population means. So the assignments are going to help you with, okay, so you're kind of pushed out into the dark a little bit and you kind of have to identify which one of these tests you should be running. So eventually that's going to be the bigger challenge. And as we go through these new tests, you want to try to set up as much as you can before you view the solutions. If you're running into any trouble, please send me an email.